Welcome to the Cosmic Savannah with Dr. Daniel Kahnemer,
Dr. Jacinta Delhaze,
Dr. Tiamiso Makwela.
And still not a doctor, Franz Ocampo.
Each episode we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Welcome back. We are back in the One Button studio at UCT.
Yes. Hello, everyone. We still haven't changed clothes
No.
if you're watching
we also
online.
have changed positions, though, and that's good.
Yes, so we fooled you all that we didn't record this all in one day.
No, of course not.
We definitely didn't.
Oh, no.
Back, what do they say? Back like we never left?
Yeah.
Yeah.
Exactly. Yeah.
Anyway.
We did live for quite a long time.
Yeah.
But then today we've made up for it.
Yeah. 3 episodes one day.
We did leave for like 7 or 8 months,
Yeah.
or pushing 9.
Was it?
It was a long time.
Nearly, yeah.
Yikes.
Yeah, so today's episode we are going to be journeying back to Oxford, where you took your Radiance team. And in the previous episode, we spoke to some of your students about their experience and what they did there. But also you took the opportunity to interview some of the researchers at Oxford.
Yeah. So I spoke with Professor Matt Jarvis, Dr. Imogen Whittam, and Dr. Anastasia Ponomareva about the research that they do as part of this big collaboration called MIGHTEE, which is what I work on in my research group also. We all contribute to, along with several others, but that's one of the big collaborations that we work on. And it's one of the big large survey projects being done with the MeerKAT radio telescope.
So Jacinta's already mentioned that she's working on the MIGHTEE Survey. So it means that there are many other surveys, like the Laduma survey, where people are working with H1 galaxies, hydrogen gas. And there's also the ThunderCat survey, where people are working a lot more with transients. And then there is...
so I wrote them down here.
Thanks, Jacinta.
So yeah, you mentioned Laduma, that's about hydrogen gas. There's MALS, which is the MeerKAT absorption line survey. And that's, if you listen to the previous episode, we were talking about the shadow of hydrogen gas, looking at hydrogen absorption. So that's about looking for the shadow of hydrogen. There's the MeerKAT Fornax survey, which we've actually talked about in a previous episode. We'll put the link to that in the show notes. That's looking at this kind of cluster of galaxies that's called Fornax, and it's got hydrogen in it, and it's also got a big giant radio galaxy at the center. There is MeerTime, which is looking at pulsar timing.
Yeah.
Do you know much about that one?
I know a little bit about it, actually, because we've spoken to Marissa Kher before.
Yes, and of course...
Alexander Anderson.
Yes, and Matthew Bales. So we've actually had several episodes on that recently.
Yeah, that's very cool stuff.
Yeah, looking at the
Gravitational waves.
Yeah, gravitational waves with MeerKAT telescope. And there's the TRAPPISM survey, which is about transients and pulsars with MeerKAT. Do you know much about that one?
No, not very
Francois?
much. No.
No. Okay, good chat.
I do optical.
But you...
I'm glad we did that.
I do machine learning and optical. That's it.
But you might know a little bit about the ThunderCat survey.
Yes, I know about ThunderCat, of course.
Okay, can you tell us a little bit about that?
It's effectively looking for radio transient events.
What's a transient?
Anything that changes in the night sky. Basically, when the pixel value changes, we go mental.
We go mental.
Awesome.
Wow.
Well, the machine
That's so
does, because you
metal.
just teach the machine.
Yeah. There we go, yeah.
Okay, so flashing things that go bang in the night, basically.
Yeah.
All right, so yeah, that's so what we mean when we're talking about these surveys is obviously like the word survey. You might think of it as like, someone sends you another Google form review to fill out, but that's obviously not what we mean when we're talking about a radio telescope. It's like it's basically it's a large program or project to look at a patch of the sky or several different objects in the sky, and it takes thousands of hours to do these observations. So that's why they're called large survey projects. And that's actually what MeerKAT spends most of its time doing, or has spent a lot of its time doing since it was commissioned in, I think it was 2018. And now we're actually coming to the end of most of those large survey projects. And so there's been a call come out recently for extra large projects for MeerKAT to work on in the future. So that's what MeerKAT spends most of its time doing. And then a small amount of time is dedicated to what we call like open time call, which is where anyone in the world can propose a project to use MeerKAT with for a small amount of time, like maybe a one night of observing or a few hours, 8 hours. And then you can just be like, okay, I want to look at this, whatever your favorite object is or whatever you happen to be doing your science on at the time. And like, let's look
Not
at
for fun, it's still for
It's
science.
for science. We're very passionate about our jobs. And so I've got a few, 2 or 3 of my own observations with
What are your
MeerKAT in
favorite
open time.
objects? Jacinta?
My favorite objects are these Nigel and Dodos. We've talked about that.
We heard
in the
about
previous
Nigel and
episode.
Dodo. Does your
And
boyfriend know about Nigel and Dodo?
Daniel, inappropriate. No, but we also point the telescope at this field called Cosmos, which I've spoken about before, so I won't talk about again. But that's probably one of my favorite fields. What's your favorite thing in the sky, Daniel?
Yeah, I don't go very deep. I mean, I'm like, these days I'm just, I have my green laser pointer and I look at like constellations.
What's your favorite constellation then?
The Eland.
The Eland, yeah.
yeah.
Also known in Western culture as the
As
Taurus.
Yes.
And in
Yeah.
South Africa in Ethno.
Yeah,
well,
I should be able to say the name, but it's got a click in the front, so into a mic is going to be a little bit
Oh, right.
closer, but I don't
Yes.
think I should.
Okay.
Gua.
Yeah. Cool. What about your favorite object to study, Francois?
Many different types. Mainly, basically now is cataclysmic variables because that's what I'm doing. They're just really cool stars where a white dwarf eats another star. It's fantastic to look at. And I like to look at basically a lot of them because that's easy to train my models on if you've got a lot.
Okay, so we're going to talk to you about that a lot more in the future. We
Yeah.
haven't talked to you about your science yet.
Yeah, it's
I
true.
want to know what training models involves, but that sounds exciting. And what about you, Tia?
At the moment, I think what interests me, not necessarily that it's my favorite one, is stuff in exoplanet science. Just-
Exoplanets, yeah.
Just how and some of the models that they're using to try and find new planets exist, outside of our own universe. Not necessarily trying to discover life, but just discovering the planet itself. Is something I find exciting.
There was that big press release just the other day from JWST where they found dimethyl sulfide.
Oh,
Yeah.
somebody
I
said
saw
this to
this.
me, but they said that they found life on another planet. I was like, that's probably not it, but let me look it up.
I was on the radio a few times about it. But basically, like as far as we know now, on Earth, the only way you can create those compounds is with life. So like phytoplanktons and microbes breaking down organic matter. So we don't actually have another way for it naturally to occur.
Cool.
And it's in quite high quantities and it's like on an ocean planet, like
That's so
in
exciting.
the habitable zone.
Oh, it's like Subnautica.
No, I don't know what that is, but yeah, sure. But yeah, it's. I mean, there are obviously, there's a lot of work to be done, and they need to figure out if there are other inorganic ways for this to happen.
So yeah, but today's episode, as we said, is about the MIGHTEE Survey. I'm talking all about that. And we'll hear from the principal investigator, so the person who kind of like leads the project, well, one of the 2 people who lead the project, Matt Jarvis, and 2 of the people who lead within a big collaboration. Like these survey projects are made of like dozens or hundreds of astronomers from all over the world. It would be chaos if you're all trying to just, work together as one big bunch. And so we kind of split into what we call like working groups, and we each work on like a particular science topic. And so then we have leaders of those working groups. And so Imogen is one of the leads of the Continuum working group, and Anastasia is one of the leads of the hydrogen emission working group. And they're going to explain everything about what that means in a moment. And I think they go into quite a lot of detail and explain a lot about that science that we're doing with that. So shall we hear from Matt, Imogen and Anastasia?
Yes, please.
Okay. With me now is Professor Matt Jarvis from the University of Oxford. Welcome to the Cosmic Savannah, Matt.
Hi, it's good to be here.
Tell our listeners a little bit about who you are, where you're from, what you do.
So I'm Matt Jarvis. I'm a professor at Oxford. I used to be an associate professor at the University of Western Cape as well, but now I'm a visiting professor at the UWC. And my main field of research is on the evolution of galaxies and how they link to the large-scale structure of the universe and the larger-scale cosmology of the universe.
You and I have known each other for quite a long time, haven't we, Matt?
Yeah, I was trying to remember how long, but it's probably too long to say online. But I give away both our ages. But yeah, so I was part of Jacinta's supervision team when she was doing her PhD.
It's actually my 15th anniversary of coming to Oxford, my 15th year.
Wow. Okay, that makes me feel much older now.
I'm older than you were when we met.
Wow. That's kind of depressing. I don't want to acknowledge that. I have no awareness of that time.
Anyway, yeah, so Matt is one of my, was one of my PhD sort of supervisory team, and we've been kind of collaborating on things on and off ever since. And now I am sitting here in his office at the University of Oxford.
Yeah, and it's great that you're here. It's nice to have you visiting. So yeah, and we continue to work together, which is even better. So I haven't put you off as part of your supervision team, so you still want to work with me. So that's nice.
So I tried to quit astronomy once, and I came into Matt's office in Oxford, and I said, Matt, I'm quitting astronomy. And he said, okay. And I said, is that it? He said, yeah. And then he somehow reverse psychologied me. And by the end of the week, I had applied for this job in South Africa, and then I eventually got it. So thanks for saving my career, Matt.
Wow, I didn't know I had that effect. I mean, I guess I always try to think, what's best for the person. And I think being an academic is hard. It's not an easy job to have. And if people have made a decision to leave and do something else, then I think they should be given the support to do it. And obviously we had a longer conversation about it after that initial remark, and you clearly changed your mind somewhere along the line. But I think it's important to support people whatever they want to do, whether it's in academia or away from academia.
I know we're getting slightly off topic, but talking about that, do you think that, like, being an astronomer and an academic, and do you think we have transferable skills that are valuable kind of for employment in other places?
Yeah, I think there's a huge amount of transferable skills. I think anyone with an analytical background that you develop doing research in astronomy, you can go into so many jobs that require that analytic thinking and just basic problem-solving techniques. Which aren't necessarily you get from a book, but you just learn to tackle problems in different ways. And even when you don't know the answer, and that's what research is, right? You're trying to discover new things, so you don't know the answer. So it is a skill set you develop. And on top of the usual more technical aspects of coding and giving presentations. So all those things are also transferable. But I think the key thing is the problem-solving approach.
Definitely. And you've used all of these skills in leading this large collaboration that I'm part of and that all of my research group are part of, and the reason why we're here in Oxford, which is called MIGHTEE, which I want to talk to you all about today. So Matt, what is MIGHTEE?
So MIGHTEE is one of the large survey projects on the MeerKAT telescope and the radio telescope in South Africa. And our aim is to use the radio wavelengths to understand how galaxies form and evolve from the very earliest times in the universe through to the present day. We do that through multiple techniques. MIGHTEE actually employs 3 different techniques to understanding the universe, all with the same data. So we use something called spectral line data to understand the neutral hydrogen content of the universe. We use something called radio continuum data to understand star formation and accretion activity onto black holes in the universe. And we also use polarization data to understand how magnetic fields evolve in galaxies over the history of the universe. So it's quite a big, wide-ranging project, but it's very exciting at the same time.
The whole point of this is to study what you called galaxy evolution. So what is galaxy evolution, and why do we want to learn about it?
So all the things we see in the universe, so stars, planets, gas even, is all contained predominantly within galaxies. And our own galaxy is the Milky Way, and we can observe that very well. But what we need to understand is how does the Milky Way come to be how it is and all the things it contains. And we can do that in multiple different ways. And the way we do it with MIGHTEE is to gather large amounts of data on a large number of galaxies and try to piece together how galaxies that we observe when they emitted the light at further way back in the universe's history, how they are different to what we observe in the current universe. So the further we look back, we're actually looking back in time. So the more distant galaxies we observe, they're part of a younger universe. And by looking at how that changes, by looking at comparing them, how they look with things that more locally around us, so what we term redshift, which is an indication of the distance of galaxies away from us, we can piece together how we get from a very early galaxy to something we observe in the present day, like our own Milky Way. So that's the overall aim. Now, why is that important? Well, I think it's important for just discovery in itself and understanding the universe that we live in. But I think in order to understand physics, we also need to understand galaxies as well. The conditions that galaxies exist in we cannot replicate on Earth. So we can't do experiments on Earth that replicate the conditions we have in galaxies or around black holes that live in the center of these galaxies. So we can use this information to understand physics as well and develop our knowledge of physics and how that might change. So one of the key components of that most people have heard of in physics is general relativity. And general relativity does act on the scales that we observe these galaxies on. And so it gives us information of how general relativity acts in the universe and whether it is actually the right theory for our universe.
So just all of fundamental physics and our understanding of existence in the universe.
Yeah, I mean, that's probably, there are other ways of doing this, but yeah, it's clearly, it's a part of our way of understanding physics. And it's an important way because, as I say, replicating these kind of physical conditions on Earth are impossible. So it's the only way we can do this by observing such distant galaxies and black holes.
Awesome. And you mentioned that you are doing this with MeerKAT. Can you say a little bit about what is MeerKAT and how you're using it to do all of these amazing studies?
Yeah, so MeerKAT is a South African radio telescope with 64 dishes in the northern Karoo, and it's the most sensitive telescope we have access to for doing this kind of study. So it's amazing in the sense that, so compared to previous telescopes, we're increasing the sensitivity and also how much of the sky we can observe, which allows us to get more precise constraints on how these galaxies evolve by piecing together things at different redshifts or different distances. So we use the radio information coming from the MeerKAT telescope because it provides a unique view on the universe. It allows us to study things like star formation in galaxies and accretion onto black holes, free of obscuration by something that we call dust, which basically is smoke in the universe, which obscures the visible light we're used to seeing, that we see the beautiful images from the Hubble Space Telescope or the James Webb Space Telescope. It can be affected by that dust or smoke in the universe, and the radio waves don't get affected by that. So we have a much more transparent view to the distant universe. And we can use that information to understand how many stars are being formed in a galaxy over a period of time. We can understand how black holes are throwing out big jets of emission of particles made up of protons and neutrons and electrons. And furthermore, we can use, as I mentioned earlier, something called spectral line information to understand where the neutral atomic hydrogen gas is. So the fundamental building block in the universe is hydrogen, and the radio wavelengths gives us a very unique view of the hydrogen content in galaxies. And we're using the power of MeerKAT to really study that over huge swathes of cosmic volume, if you like, much more in depth than what's been possible before with less sensitive telescopes.
You mentioned that you're doing this MIGHTEE survey with the MeerKAT telescope in South Africa. Can you tell us a little bit more about what is MeerKAT and why you chose to use this telescope and what exactly you're doing with it?
Yeah, so MeerKAT is the radio telescope in South Africa. And the reason we're using it for our survey is it's much more sensitive for our science than other telescopes that have been around the world or even just starting at the same time of MeerKAT. MeerKAT is kind of the perfect telescope for this very sensitive observations of the radio universe. We're using it to survey 4 different patches of the sky, which are actually chosen to be free of they're kind of holes in our own Milky Way where there's a very low density of stars and gas. So we have a much clearer view of the extragalactic universe, so the universe beyond our own Milky Way. And it's taken around 1,000 hours to start with. There is a second component that we're actually adding to at the moment, but the bulk of the survey is about 1,000 hours of time on MeerKAT telescope to observe these 4 patches of sky.
1,000 hours? That sounds like a lot.
Yeah, it is a lot, and it's a lot of data to deal with. One of the unique aspects of MeerKAT, it asks for large proposals to do really cutting-edge, big science, which requires large amounts of time to do that cutting-edge science. So it was an opportunity that we couldn't really pass up. And we had the perfect telescope with an allocation of time process that allowed us to bid for a lot of time in order to do the best science.
Yeah, because a lot of people don't realize that we actually have to compete for time with these telescopes to look at the things we want to look at.
Yeah, so you have to write a good proposal. You have to basically outline what key science you're going to do, what results you expect. Obviously, you can't predict all the results, otherwise you wouldn't be doing the survey if you knew what you're going to find. But you have to present the pathway to getting to the big science and make it as good as you can, because it's a hugely competitive process, and you have to write a proposal that is better than other people's, essentially.
And you mentioned that, this 1,000 hours, that produces a lot of data. And I mean a lot, many terabytes. So who processes all of this? Who works with this data? Who kind of gets the science out of this?
So yeah, obviously having a huge amount of data like this, we need a team of people. You can't just do it I couldn't do this on my own, even if I had the time. I don't have the requisite skill set for doing much of the data processing. So it requires gathering a large team of people with different skills in order to get the science out. So we have people working very much with the data and processing the data to make it science ready. And that's a team led by Ian Hayward in Oxford, with help from a whole bunch of people around the world, but predominantly driven by Ian. And then we have different people lead different aspects of the science. So we have working groups which are led by a variety of people, again, from around the world. And we try and split up the responsibilities, so it's not just all down to one person. So it's a real collaborative effort to get both the data out and the science done. And that's a challenge. As one of the PIs of the survey, it's my responsibility to set up that structure and to ensure it works reasonably well and efficiently in order to allow people to do the science they want to do.
Right. So MIGHTEE is the name of this particular survey or project with MeerKAT, and it's also the name of our research collaboration, the team of people who are working on the data and doing the science. And as you said, you're the PI, the principal investigator, and you're coordinating this team of 100 or so astronomers all over the world from a whole range of backgrounds and different levels, all the way from, honours and master's level of students and PhD, postdoctoral researchers, and then to, senior astronomers. Do you have any insight about that? How do you even set that up, and how do you coordinate that, and how do people work in a collaboration? Describe that for us.
It's a really interesting question. I think a lot of the way it works is on trust. And I think part of that trust comes from getting the right people doing the right jobs. And by that, I mean, not me just dictating you do this job, but assigning people to the jobs that they want to do, not the things that you think they should be doing. So there's a buy-in from all directions. So obviously you can't have a young PhD student who's new to the field responsible for the bulk of the data processing for a 1,000-hour survey. That would be unfair on them, and it wouldn't lead to any good results for the survey. So you have to think carefully about who you ask to be in these roles, and you have to then delegate that trust to them that they know what they're doing and can run that part of the survey for you. That said, I think there's a responsibility on the PI to make sure that things do run smoothly. So I'm certainly not completely hands-off. I don't just delegate all responsibility. I talk to the working group leads and the wider collaboration, often on telecons and Zoom calls, to make sure things are going okay. And I think one of the key aspects that we've really focused on in MIGHTEE is how to ensure that the younger people who are just starting out on their careers get the most out of it and get the best science out of it. And you have to allow more time for that because they're obviously less experienced. But I think the rewards are greater, and it's kind of a responsibility we have as senior astronomers to ensure that the next generation coming through have all the opportunities they can. So I think what we've done with MIGHTEE is to protect projects, science projects for students who are coming through, to make sure that there isn't an older person somewhere in the world in the collaboration that's going to steal their work. A good thing about working as a collaboration and not having a free-for-all of all the data is that you can control those things. So at the expense of possibly getting more papers out and more science out, we work very hard to balance that with ensuring that the younger students get what they need to get out of it as well. So that's a tricky balance, and it requires some difficult conversations sometimes. And I think one of my responsibilities as the PI is to have those difficult conversations, which are often with more senior people, where the students or the younger people don't feel like they can challenge older senior astronomers.
So you sort of believe in kind of essentially protecting the younger students and making sure that their best interests are prioritized?
Yeah, definitely. And I mean, obviously, you can't do everything for everyone, but that's the aim we have. And obviously, you also can't wait forever. Different students work at different rates, and you have to allow some leeway for that. But you also can't wait for 3 years sometimes, because the data will become public and other people will do it. So you have to also give the help to the students to make sure that they deliver do the science and deliver the paper in a reasonable amount of time that's good for them, but also good for the collaboration.
And that's actually why we're here visiting you this week. I'm here with four of my research students. We call ourselves the Radiance Research Team, and you and I managed to put together a grant application to it's called AFOX, the Africa Oxford, I think it's a Collaboration Catalyst Travel Award, I think is the full name. And we're very grateful for that money, which is allowing us to, facilitate co-supervision. So you're co-supervising some of my research students and this really nice knowledge share and knowledge transfer between, the University of Cape Town, the University of Oxford. And I think it's really great to have the students in particular being able to be in a different environment. So thank you very much for hosting us this week. It's very exciting, and I hope that we'll help produce some really exciting science out of the MIGHTEE data.
Yeah, it's great that the students are here and able to work with not just me, but the other people here in Oxford working on MIGHTEE. And having access to the grant to do this is really important because money is hard to come by everywhere, and particularly for student travel. So initiatives like AFOX are great for facilitating this. And the 4 students you brought with you are all great, and I really look forward to working with them this week and next week while they're here. And I think it's also important for them to get exposure to the other students in another institute like Oxford and talk to other students and other young researchers in Oxford and form their own collaborations going forward and know who, put a name to a face rather than just be this person who's in this other institute that you see the name of on a paper but don't know who they are. And it's an opportunity to actually do some proper networking and understanding where people are coming from and what they're doing and talk to them properly.
Well, thanks for everything that you've done, Matt, for hosting us and for speaking with us on the Cosmic Savannah today. Do you have any final messages for listeners?
Just that I think astronomy, particularly in South Africa, with all the growth in astronomy and the community with MeerKAT and further on for the SKA, I think there's a massive amount of opportunities. And like we said earlier, I think even if you don't end up being an astronomer, the skills you learn doing astronomy are great for so many high-tech areas and lots of other things. And it's such a rewarding thing to be involved in.
Thanks very much for speaking with us today, Matt. With us now is Dr. Imogen Whittam and Dr. Anastasia Ponomareva from the University of Oxford. Welcome to the Cosmic Savannah, Imogen and Anastasia.
Hi, it's great to be here. Hi, everyone.
Can you first just tell our listeners a little bit about yourself, who you are, where you're from, what you do?
Hi, I'm Imogen. I'm currently a Hinsey Fellow here at the University of Oxford. Before that, I was actually at the University of the Western Cape in Cape Town for 5 years as a postdoc there. And I research galaxies, and I'm particularly interested in the supermassive black holes at the center of galaxies.
I'm a postdoctoral researcher here as well at the University of Oxford. Before that, I was postdoc in Australia and the Netherlands, basically following all large radio astronomy megas, studying a neutral hydrogen in spiral galaxies within the context of evolution of galaxies.
Wow. Okay. So we're going to talk all about that in a minute and break that down. But yeah, Imogen, you and I don't really know where we met the first time, possibly here in Oxford, but where we are now, but definitely in Cape Town when you were a postdoc there.
Yeah, I can't remember when we first met, but we definitely knew each other very well in Cape Town.
How are you enjoying being back in the UK and in Oxford? And do you miss us in Cape Town?
Oh, I totally miss Cape Town. I miss loads of things about Cape Town. I miss all the people there, but also the weather. I mean, have you seen the rain in Oxford? But yeah, no, I miss Cape Town a lot.
I did cycle home from the department in Oxford the other day and get completely drenched, and my shoes are still drying.
Yeah, that's what I say to the visiting students from Cape Town University, that they didn't expect that our summer is much worse than Cape Town winter.
It's true. All right. So we're talking about the MIGHTEE Survey today, and we've just heard from Matt Jarvis, who is one of the principal investigators of MIGHTEE. And he's sort of explained to us what galaxy evolution is and why we want to study it. And he also mentioned that there's several different aspects to this survey. There's what he called continuum, and then there's spectral line, and then there's polarization. And you two are leading you're leading two working groups studying certain aspects of those. So Imogen, could you first explain to us which working group you're leading and what does that mean?
Yeah, so I lead the Continuum Science Working Group along with Catherine Hale, who's another postdoc here in Oxford. And that means that we are doing all of the science to do with stars forming in galaxies and also the emission from the supermassive black holes. So there's a whole bunch of different projects using the data, focusing on those aspects that we do.
And yourself, Anastasia?
I'm together with Dr. Anastasia Maddox, who is based in the University of Bristol, even though she used to be based in the University of Cape Town for quite some time. We are leading the H1 emission line working group, basically looking at the emission of neutral hydrogen from galaxies and study different galaxies' properties by analyzing this data.
Okay, so there's a lot of words there. Let's start actually first with you, Anastasia. You said neutral hydrogen gas. What is that?
So basically, neutral hydrogen is the building block of all the structure we see in the universe. You know, people are made primarily from water, so the H in your water is a hydrogen. Hydrogen is in the air we breathe, and hydrogen for astrophysics is extremely important because it's a raw fuel for star formation. So all the stars, including our sun, have been originally born from neutral hydrogen. We call it neutral because it is just, hydrogen can be in many states, but what we study is the first building block of the universe, which is atomic hydrogen, which only consists of one proton and electron. And when the spins of the one proton and electron flip and not align with each other, the atom emits a photon, And we as radio astronomers know exactly the wavelengths at which it emits and also the rest frequency. And that's how we can observe it coming from other galaxies.
This is the weird quantum mechanical property of atoms. They've got this weird thing called spin. It doesn't really matter what it is, but the hydrogen atom emits a little flash of light, basically. And we know what frequency that's at, and it's at 1420.4 megahertz, I think. Is that right?
1420.405 megahertz. Yes, to be exact.
Good. Okay, and so we can study this hydrogen gas with the MeerKAT telescope and with MIGHTEE, right?
Yes, absolutely. More than that, MeerKAT telescope right now is the best instrument in the world to study the emission of this hydrogen from other galaxies. It's a fantastic telescope. It's extremely sensitive to this transition, and it also has a fantastic field of view, so we can cover a lot of galaxies at the same time. So we can conduct these big surveys where we don't need to observe one galaxy and spend all our telescope time there, but we study a huge patch on the sky with a lot of galaxies in it, so we can build a large statistical sample.
Right, so we can see lots of galaxies on the sky. We can see a large patch of the sky, and we can study lots of them, and the hydrogen gas inside them. So what have we found so far with MIGHTEE?
So far, one of the largest discoveries, the first discovery of MIGHTEE Survey using MeerKAT, was finding a very large but very young group of galaxies in a completely well-known, super well-studied field. However, that group was completely overlooked using other surveys, and it was only possible with MeerKAT and with MIGHTEE Survey. Then this group was found of very young galaxies where you can see that they're just in the process of their assembly in the group, and you see all the transformation which happens to their gas disks. And we are very proud of that discovery and that study because it was also led by a master student based in South Africa, Shilpa Ranchard, whom I believe you had at your podcast before.
We did. We actually have a whole episode on this discovery, I think, but I can't remember it right now. So I'll tell you, listeners, a little bit later which episode that was. But yeah, so not only did Shilpa and the team find new galaxies, they found a whole group of galaxies, and they found them close by and in a place that has been looked at many, many times, but they just had never seen. How is it possible that it had been looked at so many times and this galaxy group had never been found?
That's the whole point of radio astronomy in general, that we are opening the wavelengths which were not accessible before with optical or infrared telescopes. An additional advantage of the spectral line, as you heard now, that it gives us not only the two-dimensional position of a galaxy on the sky, but also it gives us a third dimension, or its distance from us to the galaxy. So we can build actually a 3D map of galaxies and see if they belong in one group or if they're too far away from each other to basically interact with each other.
That's cool, a 3D map. So these galaxies had been seen before, but we just didn't know that they were close to each other and related to each other and interacting, because the hardest thing in space to measure is the distance away. So they might have been, looked close together on the sky, like the stars that make up constellations in, our galaxy, but we don't know how close they are actually together, right? And so is it correct that this 3D map helped us to realize that they were all close together and interacting?
Yes, definitely. That was the whole discovery, that these galaxies were not only galaxies on the sky, but they belong together in the one gravitationally bounded group of galaxies who are interacting with each other and share the same environment.
And I happen to know that you've written quite a few papers using this MIGHTEE data. Can you tell us anything about those?
Yeah, absolutely. Thank you. So one of the main goals of MIGHTEE studying H1 is to study the cosmic evolution of neutral hydrogen. As I said, it's extremely abundant because all the structure is made of it. However, it's extremely faint. So it's very, very hard to look at hydrogen at higher distances. We only have known so far galaxies and properties of galaxies via neutral hydrogen, which are very nearby to us. And now with MIGHTEE H1, for the first time, we can push these boundaries a bit further and study galaxies which lie, for example, 1 billion light years away from us. And that was one of my research papers which I did with the survey is to study how the H1 in galaxies is distributed as a function of its mass over 1 billion years from now, which was for the first time which we looked at it, and also measured the H1 cosmic density.
Okay, so H1, that's what we call the nickname for neutral hydrogen gas. And you were trying to detect this out to greater distances into deeper space than we've ever detected before. And you said that some of these galaxies were like 1 billion light years away. So why do we want to look that far away?
We want to look that far away because we want to build a complete picture of galaxy formation and evolution. Ideally, we want to go all the way to the beginning of the universe and understand how structure formed and how galaxies evolved in order to understand our own origin as well, how we came about to be as we are now, our own galaxy Milky Way. And we already can do this with stars pretty well. We can do it, for example, with JWST. We're now discovering galaxies formed almost in the beginning of the universe, and only with MeerKAT. And then further with SK, which also will be based in South Africa, we will be able to also trace the evolution of primordial material which formed stars and basically combine this evolutionary history of galaxies together.
Right, because like looking deeper into space means looking back in time. And so if you can look really, really, really far away, you can actually kind of almost see just after the Big Bang, right? It's like space works like a massive time machine.
Yeah, absolutely. So the deeper you look, the far back in the past you can see with astronomy. That's a cool part about astronomy, that we have this gigantic time machine.
And when you looked further away at this hydrogen gas further away, what did you find?
We find that even though the amount of stars galaxies keep forming right now is decreasing in comparison to what it was with the half-lifetime of the universe, we're finding that the amount of neutral hydrogen is more or less constant throughout the life of the universe. And this is extremely puzzling for us to understand why, if galaxies have the same amount of supply through their entire life and the formation of the universe, they're not very efficient to form stars out of this supply from about half-lifetime. So this is something which we are still trying to do better measurements and understand.
Right, so we know that kind of if you look further and further deeper into space, those galaxies further away were forming stars much faster than galaxies are now, which is in the present. And so the idea was that we should probably find more hydrogen gas, because gas is like the fuel, like when you put fuel into your car. And if you've got, well, that doesn't really work. Maybe fuel for a fire. If you've got more fuel, like, more wood, the fire will be bigger. And if you take away the wood, then there will be less fire. And we found here that the fire is the stars. And if there's, but we found that there's just the same amount of wood in the past as there is now, but there was more fire in the past, more stars, but the same gas. So weird. Do we know why?
That's exactly what we are trying to understand, that our measurements correct, and this is exactly the case. Then we need to build our models of galaxy formation evolution better to answer these questions. But it's basically one of the basic questions we are trying to answer with all these new surveys.
All right, so we don't know, folks, and that's what we're trying to research. So speaking of unanswered questions, I know, Imogen, you are working on a lot of these, and you mentioned that you are leading the working group, which we call Continuum, and that's, as you said, studying star formation and black holes inside galaxies. So tell us a little bit more about what that means and what you found.
Yeah, so it means that we're, as you said, interested in things to do with how stars form, and also things to do with the supermassive black holes at the center of galaxies. Because I think we've talked before about how essentially all galaxies have got a supermassive black hole at their center, and about 1 in 10 of those are what we call active. So this means that gas and dust is busy actually falling into that central supermassive black hole, and that's a hugely energetic process. And often you get these giant radio jets produced, which I talked to you about when I was on the podcast before. And so these form these really lovely radio jets, which are perfect to observe with a radio telescope like MeerKAT's. So we've been studying these with the MIGHTEE Survey and also studying the star formation in galaxies. So there's a whole range of different projects we've been doing.
We actually spoke to you on the Cosmic Savannah back in season 1. You were on episode 4, so our fourth ever episode, and you explained all about radio galaxies. So listeners, if you want a nice episode to compare to, have a listen to Imogen on episode 4, where she explains everything about radio galaxies. And you mentioned back then that there was this survey called MIGHTEE that was about to start with MeerKAT taking data. And now we're like 5 years into it and we've collected all of the data. So tell us what the latest updates are.
Yeah, it's really nice to be back and to see how much progress we've made in 5 years. Because as you said, back then we hadn't taken any data. Now we've finished taking all of our data. And that doesn't mean that we're in any way finished yet, because it actually takes quite a lot of time and effort to process the data. So although all the observations have been taken, we're still very much analysing the data, and not all of it is science ready yet. But we have actually, we've released quite a large section of the data. And in fact, for the continuum side, there have been 10 papers that we've published with exciting science results. And there are many more that we're still working on. So there's been quite a lot of exciting science that's come out of this already.
Yeah, it's been really exciting and I've loved being part of the team. And so I know that you've led 2 of these papers. Can you tell us a little bit about what they're about? I know it's quite a complicated topic, but maybe you could just explain a little bit.
Yeah, so the Q one has been about radio galaxies, which I spoke to you about before and are my true love, I suppose. And so, as I said, we're interested in these supermassive black holes and these jets, and particularly we're interested in how these jets are fueled. And we've been studying this with MIGHTEE, and we've actually found that it was previously thought that there were 2 different mechanisms that these jets were fueled by that were quite separate. So either they were fueled in quite an efficient way via one mechanism, or they were fueled inefficiently by a different mechanism. But we've found that actually these 2 different mechanisms aren't as separate as people have previously thought. And so our previous understanding of how this works probably isn't quite correct. And it's always interesting when you find that something's not quite right, and because it's one of those things where actually we've answered some questions, but we've come up with 10 more.
Oh, it's always the way, but that's how research goes, right?
Mm-hmm.
So, okay, so I really like how you've just described this, because I know your work is actually, as I said, really complicated, very statistical. But yeah, so you said that there's AGN, so active galactic nuclei, supermassive black holes at the centers of galaxies, stuff falling into it. We talk about it all the time on the Cosmic Savannah because it's also my area of research and the listeners know that. And you've just kind of blown my mind. I know that I am actually a co-author on this paper, but it's been a long time since I've read it. And it's actually kind of the opposite from what I teach my students in my undergrads. Hi to my 3rd years, by the way, if you're listening to this. We talk about that there's these 2 very different ways to start a fire, basically, like to start this AGN activity in the center. And you are now saying that actually they're kind of overlapping. So what does that mean? And why do we care about this? Why is this important?
Yeah, so we do think they're overlapping. As you say, this is kind of surprising. It goes against our sort of picture in the head and in the literature of what we think is happening. One thing that is key here is the reason we found a different result is that we're looking at much fainter, so less powerful radio sources, and also we're looking to higher redshifts, so that things that are further away. So we're not saying that previous work is wrong. We're just saying we're looking at different types of sources. Well, not different types, different sources. And so they're behaving a little bit differently, but we don't think they should behave differently. So it means our picture of how AGN work isn't quite right. And that's important because it's exciting, because it means that we don't really understand quite how AGN and how these jets work. And that's always exciting. There's more to find out. But it's also key for understanding all of galaxy evolution, because we think that AGN play a key role in regulating star formation in massive galaxies.
What does regulating star formation mean?
Yeah, so if you make a simulation of everything we know about astronomy, you put everything in, you start at the Big Bang, you run it all the way forward till now, you find that all of your galaxies have formed all of their stars, used up all of the fuel for their fires, as we've been saying, and there's no gas left, all the stars have formed, and they've all died, and there are no stars left. And clearly that's not true, because there's loads of stars still being formed in the Milky Way and at other galaxies around us right now. So something must be slowing down the rate at which galaxies are forming stars. And for massive galaxies, we think the key thing that's doing that is AGN activity.
So we think our understanding of these AGN is wrong, and that could explain why we can't explain why there's still so many stars forming in the universe.
Yeah, so we've known for sort of maybe 20 years that it's probably AGN that are slowing down the rate at which these stars are forming. But what we don't know is actually how that process works. So, okay, we know the AGN are slowing the stars forming, but how are they actually doing that? And there have been lots of different theories. And one of the things we think is that these AGN that accrete via or gather their gas via these two different mechanisms then affect the star formation in different ways. But if there aren't these two different mechanisms, then maybe the stars aren't affected in the way that we thought. So basically our whole understanding maybe isn't quite correct.
So you're saying that the universe is confusing and weird, and we need to understand more about physics.
Yeah, exactly. Confusing and weird is a good summary.
Awesome. Now, the other piece of work that you're doing or you have done is what we call cross-matching. So we've already talked about how there's all the different wavelengths of light, and radio light is one of them. Again, type of light, not a type of sound. I hope all of our listeners know that. And we use radio telescopes to see the radio light. We use infrared telescopes to see the infrared light. We use optical to see the optical light. And we use UV telescopes to see the UV light, right? And then we can look at galaxies in all of these different wavelengths. We can make big maps of the sky. And the challenge is to say, okay, which blob of radio light and which blob of UV light and which blob of optical light are all coming from the same galaxy. We call this cross-matching. So you have to try and look at the different wavelengths and see which goes to which. Now, you have recently published a paper where you've painstakingly done this. Can you tell us a little bit about that and what the plans are for the future and what's the ongoing work there?
So previously, we've done this cross-matching process by eye. We've literally made images and overlaid them on top of each other and by hand said, okay, this galaxy in this radio image is the same galaxy as this galaxy in this optical image. And that's great when you've got a small number of sources. For example, the sample I studied during my PhD had 300 sources. Perfect. I can happily look at 300 sources. Now the problem is, with surveys like MIGHTEE, we're detecting hundreds of thousands of sources. And it's just not possible, even if I wanted to, for me to look at hundreds of thousands of sources. So we need to come up with other ways of doing this. And this paper that you're talking about, what we did was we actually did look by eye at about 5,000 of these galaxies and do this cross-matching process. But then we used that sample to test various automated methods. So that in the future, we don't need, for the full MIGHTEE Survey, we don't need to actually physically look at everything. We can automatically match, say, 80 or 90% of them. And then only it's the sort of tricky 10 or 20% left over that we need to look at by eye.
How long did it take you to do this for 5,000 objects?
Oh gosh, I can't remember. I mean, it feels like it took forever, but probably wasn't that long. But I will tell you, I was kind of seeing radio galaxies in everything that I looked at for several weeks.
I was helping you out with this fairly recently. I think I sent you a photo of some soap suds on my kitchen bench, which I was sure looked like a radio galaxy.
Yeah, you just start seeing them everywhere.
Tell me more about these automated or like semi-automated methods.
So we can use automated methods on quite simple sources, so sources that are basically just a blob. But for the more complicated and, in my opinion, more interesting sources that have these lovely extended jets, then we do need actual humans to look at them. And for that, we've got something called MIGHTEE Zoo, where we're using the Galaxy Zoo interface, which you may have heard about from various citizen science projects. And so we're using that interface, and lots of lovely members of our collaboration, including Jacinta right here, are helping us out by doing lots of clicking on all of these different images to manually identify the correct matches.
It's related to the Zooniverse project, isn't it?
Yeah, absolutely. So we're using the Zooniverse kind of architecture for this project, but this one actually isn't public. It's just for members of our collaboration.
Yeah, so we've done a couple of episodes on Zooniverse-related projects. Unfortunately, this one isn't public. Otherwise, I would ask all of our listeners to go and help because it's a lot of work. But it does take quite a bit of knowledge of the intricacies of the astrophysics of these radio galaxies and everything to try and do the matching. But we've got a lot of students who are on board and helping, which is awesome.
Yeah, it's really great. Like you say, it's a little bit too complicated for this one to be a public project, but it's so great to have all of the students involved in helping out.
So I guess the reason why we're spending so much effort in doing this kind of what we call cross-matching is because, you need the different parts of a galaxy or an AGN or whatever it may be, they emit a different wavelengths of light. And so you really can't understand all the physics of a galaxy unless you can look at it in all of these different types of light. And now that a lot of the cross-matching has been done, what physics results have come out of this? What other discoveries have come from the MIGHTEE Survey in your particular working group?
Yeah, so as I said, there have been 10 papers which have been published, including the 2 of mine we've been talking about. Also your lovely work discovering the giant radio galaxies, which has been really great. There's been some other work looking at star formation and how we can work out exactly star formation rates from radio data. Which has been very interesting, and lots of other work as well. And there's many other projects that are underway that are nearing completion, so watch this space.
Yeah, exactly. So we'll definitely be talking to several people, especially some students coming up soon with their new results. And okay, so we know that all the data has been taken now for the MIGHTEE Survey. Does that mean we're done, or what's coming up next?
No, we're absolutely not done. This is kind of where the fun starts to some extent because we're still processing the last bits of data, but once the data's processed and once we've done all this cross-matching, that's when we can actually do all of the science. So there's some projects that have already been done, but quite a lot of the projects, they need the cross-matched catalogue over the full area, which isn't available yet because we're still doing it. And so once that's available, then all of the science projects can fully get underway. And as I say, that's where the fun starts. That's where we start getting some really exciting results, hopefully.
Yeah, super excited. And I guess, and we're also trying, we won't say too much about it because it's not public yet, but we're also trying to get some more data to do even more science with MeerKAT, right?
Yeah, absolutely. We always want more data. So watch this space for that.
Thank you so much to both of you for speaking with us today. Before you leave, do you have any final messages for listeners?
Thank you very much for listening and keep being interested in astronomy and astrophysics because it's really cool.
Well, I've recently come back to work having had a baby. Now he's a toddler running around. So I just want to say that it's possible to balance having a family and doing science research. It's not always easy, but it's going well and it's been super fun. So
that's awesome. I think there will be a lot of young women out there who will feel really supported to hear that it definitely is possible.
Yeah, absolutely. Definitely possible, particularly with the right support.
Hats off to you, though. I know that you have had many sleepless nights and you have been working really, really hard and taking care of everybody else around you. So thank you, Imogen, also for your work there. So thank you both, Anastasia and Imogen, for speaking with us today. And bye for now.
Bye. Thanks for having us. It's been really great.
Bye. Thanks a lot.
Those are really some nice interviews, Jacinta. Thank you for catching up with these world-class scientists who are contributing to what we understand and what we have in the universe. And it's quite exciting to hear that, some of our masters and PhD students from South Africa are also part of these discoveries. And I think one of the things that I'm taking away from this interview is never think you know something fully because data might just surprise you, right?
Yeah. Sure. Well, That's astronomy, right?
Yeah.
Yeah.
Pretty much.
Yeah.
And don't try and fudge your results.
Yeah.
Because if they seem wrong, you might actually be finding new science.
Nice to hear, Imogen. So, I mean, Matt mentioned he's still associated with the University of the Western Cape here in Cape Town. He used to spend quite a lot of time here. I think less these days. He's very busy over there. And Imogen was here for many years.
As a postdoc.
As a postdoc.
At UWC.
Yes,
Yeah.
UWC. Yeah.
Seems like the UWC to Oxford pipeline is well on the line.
Yeah, I
Wow.
think that was set up by Matt Jarvis, right?
Oh,
and,
is that
and
right?
that
Oh,
was
okay.
kind of the point, right? So, like you were saying, Tia, it's great to see this sort of, the South African involvement in these projects, and people like Matt working towards building the capacity here. It's really cool.
And several others.
And several others, of course.
Yeah. It was really cool to hear the updates on the research that's been going on. Anastasia mentioned the work of Shilpa Ranchod, who we spoke to in episode 43, the search for hidden hydrogen, and the work that's been done since then. And also, we actually spoke with Imogen in episode 4, all
Taking us
the
way back.
way
Yeah.
back in season 1.
I think Francois was still at school.
Francois.
Yeah, that's right. Well, yeah, it was just Dan and I as the hosts, and Simiso was a PhD student.
Yeah.
Hadn't come on board yet. And yeah, Francois was at school. I think that's actually true.
2019.
Yeah.
Oh, it
What?
is actually true.
2019?
19.
Yeah, 2019.
Yes.
Yep. Okay.
Ouch.
Wow.
Matric.
Yeah.
Wow. Okay. On black holes and radio jets.
As
So
you were.
it's really cool to see the evolution of her work as well on black holes.
Yeah.
Speaking of black holes.
yes.
Oh.
Good story. I got a good story on black
Yes.
holes. Also, there's a very good Italian author, Carlo Rovelli. Listeners, if you haven't heard of Carlo Rovelli, go look up Carlo Rovelli. He's written some excellent books. The one I read most recently was called Reality is Not What It Seems. It's about quantum gravity, or the search for quantum gravity. So,
What's quantum gravity?
yeah, all right. So we're not going to go into quantum gravity today because it's the end of the
What?
episode. And everyone's just
Start from the
listened to
beginning.
a lot of interviews. We're not going to go into quantum gravity. However, so the idea of quantum gravity is basically unifying like quantum mechanics and gravity. So general relativity, which general relativity works really well. Quantum mechanics works really well. They don't work well together. We need to find some way for them to work together. Quantum gravity is the way. Anyway, this is beside the point. Read the book. Please don't let me explain it because I'll probably absolutely murder it. But one thing which absolutely blew my mind with black holes, because we were talking about favorite objects earlier, and I think that now this has become my favorite story or my favorite object. If quantum gravity works, or if the theory holds, then in the same way as there is a sort of, like when stars collapse, they reach a pressure, like an atomic pressure, which then causes them to go supernova. So they collapse down until the atomic pressure is too much, pushes them out, and they explode.
Like when you've got like a really strong spring. And you're like, and you press it all the way, and then it goes boom, like that.
At some point it explodes, and
Yeah.
because it actually just you put too much pressure on this thing and it explodes outwards. So if quantum gravity is legit, then there is a minimum distance. There's a minimum scale, beyond which nothing can be compressed. There's no such thing as a singularity. Then there is a pressure there because it cannot be compressed any further. So when a black hole collapses, we always assume it's a singularity. If it collapses, and this is true, there is no singularity, it reaches some pressure.
Okay, so if the black hole's collapsing, it's like the spring is the
spring's getting loaded.
Load the spring as hard.
So then what's
as-
going to happen?
Yeah,
Yeah,
it's going to explode, right?
It's going to explode,
Yeah.
right? Why don't we see black holes exploding? Because, wait for it. At that density, time dilates so much that even if the explosion inside a black hole is instantaneous from our point of view, or near instantaneous, inside the black hole, it will take billions of years. So it'll be instantaneous inside the black hole,
Okay.
but from our perspective, it'll be billions of years because the time is dilated so much because of the extreme gravitational force.
So it's a bit like the moon thing that we talked
It's
about
like the moon thing.
Yeah.
a few episodes ago, how
Yes.
time, but because of the hypergravity, the dilation is so severe that it's like billions of years of explosion.
like time gets stretched so long that an instantaneous second will take
billions
of years for us to see it.
from our
Yeah.
from
So
our
it's like
perspective.
inside the, what do you call it, the Schwarzschild radius of the black hole, like
way
inside
up,
the limit of where you can
Horizon.
see. It's busy exploding,
Mm-hmm.
and it takes billions of years.
For the explosion to
we
register,
view it as billions of years
Yeah.
for it to become
that's
visible
crazy.
to us. That's my mind being
Precisely.
blown.
But presumably, considering the age of the universe, we should have and then at some point seen an explosion of a black hole.
And we may have. I mean, there's things that are unexplained.
Like
You-
fast radio
transients.
bursts and transients and
Things that go bump in the
That's
night.
true.
transient
Yeah.
over here.
The way you say
FRBs.
transient.
Yeah, there's some venom in
Well, it covers all manner of sins.
We've already talked about whose favorite object is whose. It's all, we're allowed to like them all.
Okay, right.
Yeah.
Well,
But
there we-
galaxies
that
are
was my
definitely better than
story.
transients.
That's your little good night story, listeners. I hope you enjoyed it and that you can sleep tonight.
And no one will be able to sleep ever again.
Yeah, well,
Yeah, because
yeah.
the black
knowing
hole
that
could
the black
explode
holes are
now.
exploding. Well, it is exploding now, right?
Oh, it's
Okay,
now.
right.
It's happening now. Ah!
And that is it for today. Thank you very much for listening, and we hope you'll join us again on the next episode of The Cosmic Savannah.
You can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on X, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelled SAVANNAH. You can also find us on YouTube, where you will see us and you'll also hear us. The episodes will be uploaded with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu.
Special thanks today to Professor Matt Jarvis, Dr. Anastasia Ponomareva, and Dr. Imogen Whittam from the University of Oxford speaking to us.
Thanks to our podcast manager, me, our social media manager, Sumari Hatting, Abigail Thamarain for transcription, Shaman for website updates, Emil Mainkeys for video creation, and the whole Cosmic Savannah volunteer team.
Thanks also to Mark Olnert for music production, Brian Masimola and Michal Werchek for photography, Carl Jones for astrophotography, and Susie Karras for graphic design.
We gratefully acknowledge the support from the South African National Research Foundation, the Square Kilometre Array Observatory, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, the University of Cape Town Astronomy Department, and the One Button Studio at GCT.
You can subscribe on Apple Podcasts, Spotify, wherever you get your podcast, and we'd really appreciate it if you could rate and review us and recommend us to a friend.
And we'll speak to you next time, The Cosmic Savannah. Yikes.
Anyway, moving on. Let's never
Sorry.
talk about that again. We do love you, listeners, and we know that you want us back. No, I'm just going to stop.
MeerKAT is.
You said MeerKAT.
Oh,
is MeerKAT.
okay. So yeah, MeerKAT is one.
Yes.
Okay.
Okay.
He's
I thought we might leave that
no,
to the
no,
end.
I'm doing it now.
Okay, Mary.
Bye-bye.
Wow. Tell us how you really feel, Tia.
Oh,
I'm tired.
And scene.